Hi everyone, welcome to our video on continuity, where we will be looking at continuity at a point. So we have a kind of general definition of continuity. Informally, we say a function is continuous if we can draw the graph without lifting our pencil. So if you draw it left to right, okay, so say we have our graph, like something like this. Well, I could draw that left to right without lifting my pencil. Something like this, there we go. Okay, so left to right, I could draw both of those without lifting my pencil. So we would say it's continuous everywhere. Well, if you have to lift it up to continue drawing, like if I had to do something like this, so I had to lift my pencil to draw the gap there, well, then we know it's not continuous at that point. Well, formally, we can define continuity at a point by these three rules that need to hold, or these three conditions. So all we have to do is make sure that f of a is defined. We have to make sure that the limit exists. And then we also have to make sure that the limit is equal to the function at that value. Okay, if it is not continuous at a, we say that f has a discontinuity at a. So for this example, example 1, let's determine the points at which the following functions, really just function, sorry, that's a typo, just function, f has a discontinuity. At each point of the discontinuity, state the conditions in the continuity checklist that are violated. Okay, so just kind of drawing this from left to right. If I were to draw it, well, it looks like that open dot would mean, so the open dot means there's a gap in the graph. So they put the open dot to really make sure we see it, because otherwise we couldn't really see it if all they did was something like that. Maybe we missed that. So they put a big open dot to make sure we know there's a gap. Okay, so that means I did have to lift my pencil to continue drawing. Okay, so that means it is discontinuous. Discontinuous at ... at x equals -5 is the first one. And then it says, well, what rule did it violate? So that's we just did the basic rule where I said we had to lift up our pencil. Well, which one of these did it fail? Well, if there's a big open dot and there's no other solid dot, that must mean that f of that value of at -5 is not defined. So we have f of -5 is undefined. So that's the reason why it's discontinuous formally. Okay, so it's got to be one or multiple of those. Okay, so, and they might say list all of the ones that fail. So for instance, this one, it's undefined. At -5, notice the limit would exist, because from the left and from the right, it looks like it's headed toward 4. Okay, but then 3 is going to fail automatically because the f of a is not defined. So it fails both rule number 1 and rule number 3, where the limit as x goes to -5 of that function does not equal f of -5. Okay, because f of -5 is undefined. This one looks like it would have been 4, so 4 does not equal an undefined. Okay, so there's the first one. And then I'm just going to change my color to organize it a little bit. So after x equals -5, it looks like I could continue drawing until I get to x equals 0. And then we have that open dot. We have an open dot right there. And then that is a solid dot. But either way, I had to lift up my pencil to get that. Okay, so that means it is discontinuous at x equals 0 as well. And then, well, again, informally, we had to lift our pencil, but based on these conditions, let's see which ones did not work. Well, number 1, it is defined. So notice f of 0 would have been 6. F of 0 is 6 because of that solid dot. So number 1, it was defined. However, the limit does not exist because from the left side and from the right side, we don't get the same number. So really, number 2, the limit from, and that's, I'm going to write it like this, the limit from the left of 0, so the little negative symbol, does not equal the limit from the right of 0, which means the limit itself does not exist. So the limit as x goes to 0 of f of x does not exist. Okay, so it fails number 2, and if it fails either 1 or 2, it automatically will not hold for number 3. So number 3, because I have a limit that does not exist, instantly the limit as x goes to 0 of our f of x would not equal the f of 0. Okay, because f of 0 was 6, but this is undefined, or this does not exist. Okay, so that means that number 3 is not going to match. Okay, and let's do, it looks like there's one more. So continuing drawing left to right, I have this open dot, and then I do have a solid dot, and then it keeps going right, and then that looks like that's the last point where we have a discontinuity. So it looks like we have a discontinuity at x equals 2. And the reason why is, well, let's see. Well, notice f of 2 is negative 2, so that one is defined. So step 1 in this is clear. Then we move on to step 2. Notice that exists. Okay, so I'm going to just put it in this graph. Notice the limit as x goes to 2 is 2 because from the left, it's approaching that y coordinate of 2. From the right, it's approaching that y coordinate of 2. So both 1 and 2 were held, the conditions held in this checklist. However, these values are not the same. Negative 2 does not equal 2, so it's really just the third one only that makes it discontinuous. The limit as x goes to 2 of f of x did not equal f of 2. Okay, so those equal different numbers. Okay, so anyway, so I think using the informal definition is always very easy to get started with these types of problems, but then afterwards we have to formally answer it using our math definition there. Okay, anyway, so let's look at another problem where they're looking at a continuity at a point, and then we'll use our checklist to justify our answer. So in this one, they gave us a function, and then they want us to plug in the value of 2 and see what happens. Okay, so all we're going to do is go through the checklist. So I want to see what f of 2 is. So f of 2 is 2 minus 4 under square root. This is an issue. If you have a square root with a negative underneath it, this is an imaginary number, so it's not real. And all we care about is real. Okay, so if it's not real, then what we have is an undefined in the real. Okay, so it's not real. So that means our number 1 instantly is no good. So it's not defined in the real. So not real, let's say not defined in the real numbers. Okay, so that when we say defined, we're considering just the real numbers. Okay, so a negative in a square root is going to be an imaginary. Okay, so that means this is not continuous. So instantly we can't answer this. It's not continuous at the value. And they used a equals 2. You could say x equals 2 if you want. So it's really just a different type of notation. It's strange sometimes what they use. Okay, so it's whichever one. So at x equals 2, or this is really just saying plug x into there, or plug the a into your x there for the 2 value. Okay, anyway, so it's not continuous because this one failed. Well, the limit is also not going to exist because, so the limit as x goes to 2 of f of x does not exist either. For one reason, you could graph this. I'm not going to use a calculator. I'm just going to go ahead and graph a real quick one. It would look something like this. Okay, so if you wanted to, you could plug it into a calculator. I'm just going to save a little time. So this is what this one looks like, and then that point, I didn't label it, that is 4, 0. And so 2's over here somewhere, but there's no graph for it. So here's where 2 is, but there's no graph. So from the left or from the right, there's nothing. So that's why this is a does not exist. It's kind of the same reason why this one was not real. There's no graph left of x equals 4 in this problem. Okay, so that could help too with these. So you can always plug it into the calculator to see what it looks like. And then, well, number 3, because both of those were bad, well then our limit as x goes to 2 of that f of x does not equal f of 2. So all 3 of our conditions were wrong or were not fulfilled. Okay, so there's that. So sometimes they're real nice where it's really just the first one doesn't work and that's it. All right, but anyway, let's see one other where we're looking at a single point. So in this problem, they're using a is 3. So let's go through our checklist. So step 1, is it defined at 3? Oh, and it's G instead of F. Let me change that there. Okay, so g of 3, well, that would be this bottom piece, because this is where I have 3 is greater than or equal to 3. So this is where that inequality is true. So that means use this bottom piece. So that means we have 3 squared minus 2, which equals 7. And so because this is a number, we know that g of 3 is defined. Okay, so the condition 1 is good. Okay, so if you get a number out of this, it is defined. So if you divide by 0, if you get an imaginary, then we have a problem. Okay, and then moving on to our next step. Well, actually, let me move that over a little bit to the left, give myself plenty of room. So step 2 is to show that this limit, or to see if this limit exists at that value of 3. So we want to see, and it's g of x. Okay, so we want to see if this exists. Question mark. So the way that we do that, well, check the left and right hand side. It's really making sure, is this true? Does the limit as x go from the left of that g of x equal the limit from the right of that g of x? Okay, so that, another question mark. So we want to see if this is true. Okay, well, to plug this in, so the one that we're using slightly from the left would be the top piece. So that means I just need to plug 3 into the top piece. So I'm going to put that work right below it. So 3 squared is 9, but let me show the 3 squared. Okay, so actually let me go ahead and box that too. We'll do this one in blue. So this, remember, means slightly left of 3, and then get as close as you can to 3. So that would be using this piece. This is slightly left of 3 and getting as close as we can to 3. Okay, so I want to plug it into those x's there. So I have 3 squared plus 5 over 3 minus 1. And then 3 squared is 9 plus 5 is 14. 3 minus 1 is 2, so we'd have 14 over 2, which eventually becomes 7. Okay, so I didn't give myself the biggest amount of space, so sorry about that. So I just wanted to get that done with. So you can always use those parentheses 2 to help, but it was 9 plus 5 is 14. 3 minus 1 is 2, so 14 divided by 2 is 7. Okay, and then this one on the right, so we want to see if this is still equal. So this means plug your piece in that is slightly right of 3. Well, that would be this bottom piece, because 3 is slightly bigger than 3. The 3 with the little positive is slightly bigger than 3. And then we want to see what happens when we get as close as we can. Well, that is 3 squared minus 2, which is 7. Okay, because these two are equal to each other, check, that means our step 2 is met. Our condition is good. So the limit as x goes to 3 of g of x does exist. Check. Okay, so step 1 and step 2 were met. Step 3, okay, so I'm going to put that over there. Our step 3 is to just check what happened with your step 1 and your step 2. Were they equal to each other? Well, the step 1, okay, so we want to see, is this true? Does the limit as x go to 3 of g of x equal g of 3? Well, yeah, this is true because this limit we found to be 7. And then g of 3 we knew was 7 as well. So 7 equals 7. So that means all 3 conditions were met. And so that means this function is continuous at that value of 3. So it is continuous at, I'll just use a. But again, it's really like x. So it is continuous at 3 because all of these were met. So those were our 3 steps. I'm just highlighting the 3 conditions as stated here, but instead of f, it's g. Okay, so g of 3 is defined. The limit as x goes to 3 of g of x does exist. And then the limit equaled the g of 3. So everything was good. Okay, so that's it. So when it's at a point, so if it's at a point, we always just go through these 3 steps. If it's not at a point, we'll deal with these in the other video. Okay, so we'll put a pause on it. Okay, so remember, if it says at a single point, we just go through the checklist, 1, 2, 3, and go through it and verify all of them. Okay, anyway, so that's it for now. Thank you for watching, and I will see you next time.